Welcome to Study Loop.
To show that the smallest angle that the orbital angular momentum vector L can have with the z-axis is as shown, what we're going to do is we're going to consider the fact that the magnitude of angular momentum, capital L, is equal to the square root of the angular momentum quantum number, little l, times L plus 1, all multiplied by Planck's constant h bar, where n is the principal quantum number here because L goes from 0 to n minus 1. L sub z is equal to m sub L times Planck's constant, where m sub L is plus or minus a 0 all the way up to plus or minus the value of L. So we'll let psi be the angle between L and LZ with the z-axis. So cosine of phi, excuse me, I said psi, but cosine of phi is equal to L sub z over L. So therefore phi is equal to the inverse of L. Okay, so now we can use our expressions. So let's replace, we're going to L sub z equal, we said it's m sub L times h bar, but m sub L is just some value of L. So this is L times h bar. Okay, so this is inverse of L h bar divided by the square root of L times L plus 1 h bar. So the h bars cancel, so we're left is cosine of phi of L divided root of L plus 1. So the maximum value that L can be is n minus 1. That's the maximum value of L. So let's replace L with n minus 1. Its maximum value is cosine minus 1. Of n minus divided by root again. So we're replacing minus 1. So we have n minus 1 times n minus 1 plus 1. So this would be n minus multiplied by n minus 1 plus 1, which is just so n times n. That's what we were asked to show. So there's our solution. Part B. All right, so for phi L to be maximum, L sub z over L must be negative, must be a negative sign. So therefore, for part B, is equal to the inverse cosine of negative minus 1 divided by the square root of minus 1 times n, times n times 1. Okay. So we could say that this is our corresponding expression, but we could simplify this a little bit. So this is equal to the cosine minus 1. So we have 1 divided by root of n times n minus 1 minus divided by root of n minus 1. And that's our expression.